In May 2025, Google's Quantum AI Lab, under the leadership of Craig Gidney, published a groundbreaking paper that sent shockwaves through the world of cybersecurity and technology at large. Rather than announcing a new quantum computer, the team unveiled a comprehensive blueprint for breaking RSA 2048 encryption, the very foundation of global digital security, using a quantum computer that suddenly feels much closer to reality than anyone had anticipated. This wasn't just a theoretical exercise or a distant possibility, it was a credible, meticulously detailed threat that instantly accelerated the timeline for quantum supremacy, sending ripples of concern through individuals, corporations, and governments worldwide. Overnight, the conversation shifted from if to when, and who would be ready when the quantum era arrived. Until now, experts believed that breaking RSA 2048 would require a quantum computer with 20 million qubits, a technological milestone thought to be decades away. But Gidney's new approach slashes that requirement to under 1 million qubits, a number that aligns with the ambitious roadmaps of today's leading quantum hardware companies and makes the threat feel immediate. The paper, published openly on ArXiv, lays out a step-by-step method to factor a 2048-bit number, the gold standard for encryption, making the process more accessible to researchers and adversaries alike. The implications are profound and far-reaching. Quantum mechanics, once considered an abstract curiosity of physics, has now become a practical and potentially disruptive tool for dismantling the digital locks that protect our most sensitive information. This isn't a bug or a flaw in our computers, but a fundamental truth about the universe itself. Classical machines simply can't compete with the probabilistic, parallel logic of qubits. For centuries, the limitations of classical computation were a mere scientific curiosity. Now they've become a security vulnerability embedded in the very fabric of reality. The publication serves as a final warning to the world. The era of quantum complacency is officially over, and the race to adapt has begun in earnest. The question is no longer whether a cryptographically relevant quantum computer can be built, but who will build it first, and how the rest of us will prepare for the consequences. The very foundations of the digital world have been shaken, and the urgency to secure our data has never been greater. The countdown to quantum disruption has begun, and the world is watching, waiting, and racing to respond. To understand Google's breakthrough, you need to know what it targets. RSA 2048, the cryptographic system securing much of the internet. Its strength lies in the difficulty of factoring large numbers, a task classical computers would take billions of years to solve. Google's blueprint doesn't brute force the answer, it uses quantum mechanics to shortcut the math, exploring solutions simultaneously. This isn't just a faster computer, it's a fundamentally different way of computing. The 2048-bit standard was chosen for its supposed long-term security, but Google's work erases that safety margin. The difficulty of factoring isn't a law of nature, it's a limitation of classical technology. A large enough quantum computer sees a solvable puzzle, not an impenetrable wall. The security model of the modern internet is now in question. The scenario described in Google's paper is known as Q-Day, the moment when a quantum computer becomes powerful enough to break the encryption that protects nearly all of today's digital information. It's a term that signals a seismic shift in cybersecurity, a day that could redefine how we think about privacy and trust online. Until recently, Q-Day was seen as a distant, almost theoretical worry, something for future generations to handle. But Google's new blueprint suggests this day could arrive as soon as 2030, much sooner than most experts anticipated. The threat isn't just about future data being at risk, it's retroactive. Everything encrypted today could be vulnerable tomorrow. Malicious actors are already collecting encrypted data, storing it in hopes of decrypting it once quantum power becomes available. Sensitive information, from personal messages to state secrets, is being stockpiled for a future breach. On Q-Day, decades of secrets, financial records, government communications, intellectual property, could be exposed overnight, with consequences that ripple across industries and borders. This looming threat accelerates the need for urgent, coordinated action across the globe. Organizations can no longer afford to wait. Quantum hardware companies' roadmaps now resemble countdowns, not just marketing slides. Every milestone brings us closer to Q-Day. Migrating to new cryptographic standards is a massive, complex, and expensive undertaking. For many, the 2030 deadline feels almost impossible to meet without immediate, large-scale mobilization. Q-Day transforms quantum computing from a scientific curiosity into a full-blown global security crisis, demanding attention from governments, businesses, and individuals alike. The vulnerability isn't just in our software or hardware, but in the very mathematics that underpins modern encryption. Quantum computers threaten to unravel the foundation of digital security. A cryptographically relevant quantum computer would mark a true point of no return, capable of retroactively breaking protections on a global scale, leaving no digital secrets safe. The warnings are no longer theoretical or confined to academic circles. They are urgent, real, and now making headlines worldwide. Google's paper doesn't just raise the alarm, it makes the threat concrete and imminent, forcing the world to pay attention. The race to secure our digital world is on. The clock is ticking, and the stakes have never been higher. At the heart of this threat is Shor's algorithm, devised in 1994 to factor large numbers exponentially faster than classical computers. For years, implementing it at scale seemed impossible. Early estimates required millions of perfect qubits. Real-world qubits are fragile, so error correction is essential, multiplying the hardware needed. Google's 2025 paper changes the game, optimizing Shor's algorithm to run with under 1 million physical qubits. Innovations like magic state cultivation and approximate residue arithmetic dramatically reduce resource requirements. The result? Factoring RSA 2048 in about a week, with hardware that's now within reach. Shor's algorithm is no longer just theory, it's a near-future engineering challenge. A powerful algorithm needs a powerful machine. Google's paper outlines a modular quantum computer architecture, balancing computation and qubit fragility. The design separates a hot compute core, where active operations happen, from a cold storage region for idle qubits. Innovations like yoked surface codes allow dense, efficient error correction, making the sub-million qubit target feasible. The blueprint calls for aggressive but plausible specs, 0.1% error rates, microsecond cycle times, and rapid control systems. These are at the edge of current capabilities, but not impossible. By detailing both the algorithm and the hardware, Google provides a roadmap from theory to reality. The era of practical quantum attacks is approaching. Google's breakthrough makes the shift to post-quantum cryptography (PQC) urgent. PQC algorithms, like those standardized by NIST in 2024, are designed to resist both classical and quantum attacks. Migrating global infrastructure from RSA to PQC is a massive, complex task, updating everything from servers to embedded devices. Experts now warn systems using classical cryptography should be deprecated after 2030 and banned after 2035. The store now, decrypt later threat means even data encrypted today could be exposed tomorrow. Securing the future isn't enough. We must also protect the secrets of the past. The only true defense for old data is to ensure it's obsolete by Q-Day, a luxury few have. The PQC transition is a race against time. The stakes couldn't be higher. Google's paper is a blueprint, not a working machine, yet. No million-qubit quantum computer exists today, and building one is a monumental engineering challenge. Achieving the required qubit fidelity and stability at scale is the biggest hurdle. Error rates must remain low across vast numbers of qubits, despite manufacturing and environmental challenges. The classical control system must orchestrate error correction in real time, with microsecond reaction times. Manufacturing a million-qubit chip is likely impossible with current tech. Modular approaches and interconnects are needed. Each step, materials, fabrication, integration, requires breakthroughs still in development. The theory is clear, but the path to reality is steep. The last line of defense before Q-Day is engineering. The race is on, and the world is watching. Breaking encryption is just one application of quantum computing. These machines could revolutionize medicine, materials, science, finance, logistics, and AI, solving problems classical computers can't touch. Quantum computers won't replace your laptop, they'll work alongside classical machines as specialized co-processors. The journey is uncertain, real-world machines will face unforeseen challenges, but the direction is clear. We're moving from if to when. We must urgently defend against quantum threats while preparing to harness their potential for good. The future is quantum, and it's coming fast. The world must adapt or be left behind. The Google paper's deepest impact may be philosophical, not just technical. It challenges us to rethink the very foundations of what's possible, pushing us to question the boundaries between science, technology, and even our own imagination. For centuries, our technology has relied on classical physics and binary logic, systems built on certainty, predictability, and clear-cut answers. These tools powered the Industrial Revolution, the digital age, and the world as we know it. Quantum computing, however, lets us engineer reality at its most fundamental level, using superposition and entanglement as tools. It's a leap from manipulating information to shaping the very fabric of nature itself. By manipulating qubits, we're not just flipping bits, we're choreographing the universe's hidden rules, orchestrating possibilities that were once confined to theory and imagination. The ability to break RSA 2048 is just the beginning. It's a signal that the old walls of digital security are crumbling, and a new landscape of challenges and opportunities is emerging. Problems once thought impossible may yield to quantum solutions. From simulating complex molecules to revolutionizing optimization, quantum computers could unlock answers to questions we haven't even dared to ask. The real shift is realizing that impossible is often just a limitation of our current technology, not a law of nature. Quantum breakthroughs remind us that progress is born from challenging assumptions. Building a large-scale quantum computer is a philosophical milestone, humanity's first step as active participants in the universe's deepest laws. It's a testament to our curiosity and our drive to shape the future. The 2048 qubit test is both a warning and an invitation. It urges us to prepare for new risks, but also to embrace the unknown and explore uncharted territory. The quantum era is here. How we respond, whether with fear, hope, or bold innovation, will define our future and the legacy we leave for generations to come.